Okay, so we learned something important here, even if by a bit of a blunder, that's okay. We learned that whenever we see a binary number, if they ask us to represent these numbers, if these could be positive or negative numbers, basically, then we know if the first bit is a 0, it means the number is positive. If the first bit is a 1, it means the number is negative. Right? That's true for 2's complement and for simple sign bits. Okay, so that's important one. And I guess you guys won't forget that now because we kind of stumbled upon it. Yeah. So that's okay. And number 2, we just do the usual 4-step method. So I'm going to do this one carefully to make sure everyone gets it. Step 1 is to add -1 in binary. That's what we did here. That's what we're still in the process of doing right now. And only 4 rules we need are written here. 0 plus 0 is 0, 1 plus 1 is 10, and so on. All 4 are written here. So let's use these to complete adding -1 in the old-fashioned method. So again, if I lose anyone here, just stop me, right? It's important we all get this part. 0 plus 1 on the extreme right just gives us 1. 0 plus 1 again gives us 1. 1 plus 1 gives us 10, so that is 0 carry 1, just like the old-fashioned method. Then we have 3 ones. 1 plus 1 plus 1 gives us 11, according to one of the rules on the side. So carry a 1. That's 1 carry 1. 1 plus 0 plus 1 is 10. So 0 carry 1. 1 plus 0 plus 1 is 10 again. 0 carry 1. That's the same thing. So 10. 0 carry 1. And the last thing is 11. Yeah. So we write the entire 11 here, but the last digit is cut off, basically. So the answer is whatever we have in the quadrant of the bottom right. That thing there. So that is now the end of step 1. So that's the answer to the end of step 1. Step 2 is to invert all the digits. So that we can do. Maybe I should write here step 1. That was step 1. Step 2 is inverting the digits. So I'll just write here 0, 1, 1, 1, 0, 1, 0, 0. Okay, step 3 was to convert this to a decimal number, right? So we can do that. Convert that to a decimal number. For that, we will get 2 to the power 0, 1, 2, plus 2 to the 4, 2 to the 5, plus 2 to the 6. Okay, and we can check what that is. 116, thank you. So that's 116. That's calculator work. We got check that. And step 4 is to just consider that to be a negative number. So I'll write it up here. Step 4 will be to write this as negative 116. Negative 116. Yeah.
And 1 plus 1 plus 1. It's 11, right?
It's 11.
So why do you think why do you secret? Why do you secret?
Okay, so we end up getting 11, so I wrote the 11 here.
Yeah.
But because both of these are 8 bits each, the final answer needs to be only 8 bits.
Oh.
So anything extra, we just cut it off.
Okay. And that would be the sign. Oh.
No, that's not the sign here. This is just part of step 2.
Okay.
Yeah. So step 3 is to then consider that a positive number and convert it to a decimal. Okay. So you guys can check number 3 at home. Just curious though, what answer did you guys get? Did anybody reach there yet? Yeah. Negative, that's 65. Negative 65. Okay, so you guys can check that at home. I'll also check that. That one shouldn't be too bad, I think. But anyway, does anyone want me to do that one? Yes. Okay, let's do that. All right, so if you're taking this down, you can take it down. I need to erase and make space here. Give you a moment to write or take pictures or whatever you're doing. Yeah, we do this. So first you got it there physics. Then mathematics, then you got to know masters in physics. So you specialize in use almost after that, comes to the specializing further. The line is now measurement theory and quantum mechanics. It's so interesting for measurements. Yeah, it's a good question. So I'm not used to people that somehow actually worry about what I'm going to do. People don't know you answers get but it was like there's this burning question. This thing called the measurement problem, and then trying to figure out how it actually is. And it's a very fundamental problem in how nature works. It's almost like spiritual, it's quite strange. And I just trying to figure out what this is. That's what drove me on this way. Yeah.
When you speak to other people,
It's not too many, but yeah.
yeah, so like when you speak to them, what are they looking for? Like, to say, mind, or
Most people are doing it because of utility. Much of using people are trying to research today are not making utility. Just because of dynamics.
so basically, they're not
Make gas and
states of.
Similar kind of thing, yeah. Similar kind of thing. So here's like trying to figure out how to use synchronization of words, a word which can be 0 and 1 at the same time. How to use that to update Google's computers, things like that. Basically to make them better, more efficient, and some of it is dangerous as well, because if they crack that properly, it means that all encryption systems in the world is cracked. That means no one's paying details and safe, nothing is safe anymore. So there's like ethical things going on with it as well.
They're still teaching this.
Okay.
Yeah, so it needs to be both senses. One is so that as soon as people learn how to do this, other people need to quickly learn how to do it. So that's obvious. Basically safe. So it's like two sides going on at one time. So all people. Yeah. That's the thing. So other people are working on it. That's a fact.
100 gigs. 100 gigs. I remember, bro, Chris was like 2 years ago, 3 years ago. I was like, yeah. Because I get 50, yeah, 59. I don't require so much. Okay, I need a sector.
Okay, guys, I'm doing number 3 on the board. I'm going to do it quietly. If you're still busy with it, that's okay. If you need me to explain anything, just stop me. Okay. All right.
Yes. Yeah. That's the bed. Yeah. Let's go from your exposition. Share everybody. Let's get boss. Let's see what I was supposed to do. No, I cannot. Okay, I'm going to.
Okay, guys, any questions? Number 3. Most of you getting comfortable with it now?
Yes.
Perfect. Okay. So let's see what else we need to do today. Actually, just if I can get through just 2 more things with you, which shouldn't be too long. The first is this table, which is to try to understand how many different things we can represent using standard numbers of bits used on computers. Right, so processors usually you don't see 8-bit processors before, that's very slow. 16, 32, 64, we usually seeing bigger ones, right? 64 is like baseline at the moment. Okay, but anyway, let's look at 8 bits and we'll see why increasing the number of bits helps us. So with 8 bits, how many different things can we represent? That is an important question. And we'll look at this visually. So 8 bits, let me just draw here. Let's start very simple. Let's suppose we had 1 bit only, a computer with 1 bit. So if I had a computer with 1 bit, it will just be either 0 or 1. I'll represent it as a dash here. That could be 0 or 1. So how many different things can I represent using 1 bit? Ready? If I'm encoding it, like let's say we want to represent different species of trees, for example, and the only thing I have is 1 bit. So how many different species can I encode using 1 bit? Right? The answer is 1. Sorry, 2. Because we have the possibility to encode 1 as a 0 and the other as a 1. Right? So 2 possibilities. Right? So with 1 bit, let's write it here like this. 1 bit, what's that? 1 bit, we have 2 possibilities. Okay, what about 2 bits? If I had only 2 bits, how many species of trees could I encode in 2 bits? 4. Right? Let's think about that. One of them could be encoded as 0, 0. The other one could be 0, 1, 1, 0, and then 1, 1. Those are 4 distinctly different things I can represent. So that's 4 possibilities. Okay, so it starts getting a bit more complicated now, but let's see if we can keep this going. 3 bits, how many things can I represent? 8, right? We can count them and check. It's going to work out to be 8. And it gets a bit complicated, but if you list it out, you'll see 0, 0, 1, 0, 1, 0, 1, 0, 0. Keep listing all of them out, you'll eventually get 8. So 8 possibilities. Okay, so we can kind of see a pattern here. Let's write the pattern on the side. What if I said the possibilities is equal to 2 to the power of how many bits I'm using? Right, does it work out? So for the first one, it's 2 possibilities. 2 to the power 2 bits, that's 4 possibilities. 2 to the power 3 bits, that's 8. So it works out like this. So if I had 8 bits, let's see what I can do with it. That will be equal to 2 to the 8, which is what? 256, I think. Someone just confirm that. It is right. 256. So I could encode 256 different species of trees into this, into an 8-bit string of bits. Okay. So let's suppose I had 16 bits. I'm not going to know this number. It's going to be massive. It's going to be 2 to the power 16, which is, I don't know. 65,000? 536. Okay. So that's a big number. That's a lot of different trees. It doesn't have to be trees. I'm just using that example, but it can be anything as long as they're distinctly different. So now I'm showing you guys this because then we can understand this table a lot better. So if we were to use 8 bits, we can represent by numbers 0 to 5, right? Even though our example, even though we know 2 to the 8 is 256, if we're including 0 as one of the possibilities, that's one of them. So 0 to 255 is still 256 different distinct possibilities, right? Okay, and the same is true for all of these. 16 bits, it's just 2 to the power of the number of bits, minus 1 because 0 is one of the possibilities. So that's what unassigned range means. It just shows us what we can represent. If you're representing only positive numbers, the 2's complement range is actually the same number of possibilities. Right? So 8 bits is 2 to the power of 8, which is 256 possibilities. From this number to this number, if you count, it's going to be 256 different possibilities. Right? So by including negative numbers, we're limiting the range of numbers we can go to. But if we increase the number of bits enough, you see we still have massive numbers we can use. Yeah. And this is like uncountably massive. What? And that is 64 bits. Okay. So does everyone kind of understand what's happening in this table? All those who are actually listening to me, do you understand what's happening? Yes. Okay. Right. Some people are just like down and ask if you understand, and they look up for the first time in 3 years and they're like, I don't know what's happening. Okay. So this is the last thing I'll do with you guys today. It's quite simple, quite straightforward. Just adding numbers in binary, whether they are positive or negative numbers. Actually, we've kind of done most of this already. So this is going to help us a lot. I'll give you some very quick examples here. They've given us one simple one. Let's say, for example, if I take 15 minus 5, right? If we do that straightforward, we get 10. But does this work in binary as well? We need to know how to do this in binary. So 15 minus 5, we need to first represent both of these numbers in binary and then just add them together the way we have been doing. Right? So do you guys want to do that by yourselves or do you want to do it together? Do it together. Okay, let's do it together. I'll just do this last example, then we can go. So we need to first represent these two numbers in binary. So I'll do 15 first. I feel like I need more space for this. So let me just open up a whiteboard. The section, that's yeah. Ready to run already. Okay. Almost done. But you can leave whenever you need to. I'm not gonna hold you guys back. Okay. All right. So now 15 minus 5. I'm gonna quickly do this. Quickly. Guys, I just need a few more minutes, then you can start talking stories. Almost done. 15 minus 5. So let's first convert 15 to binary. Do this one quickly. Now what's happening here? How do I take this thing out now? Oh, down here. No. Can I just move one side, please? Yeah. Okay. 15 minus 5. 15 in binary. Does anyone know what that is? 15. 1, 1, 1. 1. Oh, yeah, you're right. That's 15, right? It's just 4 bits. Thank you. So it's 15 in binary, but let's now represent it using 8 bits. 2, 3, 4. Just add 4 zeros in front. Minus 5 in binary, we need to represent. This is going to be a 2's complement thing. So we can do this quickly because it's an easy number. So we can write, I'll do this on the side. 5 is the same as 4 plus 1. Right, so that's 2 squared plus 2 to the 0, which is going to be, let me think for a second. 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0, which is 1, 0, 1 in binary. So that's 5 in binary. Quickly, but you guys can do it slower if you need to. So now let's represent this using 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now what is the first step here? It was to invert all the digits to convert this into a 2's complement number. Step 1 is invert all the digits. So I'll write this 1, 1, 1, 1, 1, 0, 1, 0. Okay, that was step 1. Step 2 is to add 1 to this number in binary. So I'm going to do this in one go. You guys can do it the long way if you want to. Why does this keep happening? 1, 1, 0, 1, 1. So that's not a too difficult one to do. And I lost the point of what I'm doing now. 1, 2. What is step 3 here? Add 1 to the number. Sorry?
Add 1.
Add 1. That was the last step.
When you invert it.
See, I inverted already. I added 1.
And then we convert that to a decimal. No.
Sorry.
Just is one.
Oh, so that was step 1.
Yeah.
So this is step 3.
Yeah.
Okay, so we have keep saying. Okay, so this is the thing. This is -5 in binary. Okay, so now to do this thing here, 15 minus 5, I just add the 15 to -5, which I worked out at the bottom. 1, 2, 3, 4, 5, 0, 1, 1. And we'll check our answer at the end to make sure it's right. So let's add this quickly. 1 and 1 is 10. 1, 1, 1 is 11. 10, 11, 10, 10, 10, 10. Okay. So that should be the answer. 0, 0, 0, 0, 1, 0, 1, 0. That should be the answer, but let's just check. We can check it because we know the answer to 50 minus 5 should be 5. So the answer we got, if we convert back to decimal, should give us 5. So I will check that quickly. And this is going to be 2 to the power, if the single right. 1 plus 2.
10.
Sorry?
10.
10, sorry. We should get 10. Okay. 2 to the 1 plus 2. Is that right? 0, 1, 2. Okay. So this would be, yeah. So it will work out. Okay, so this is our answer here. Plus. Okay, I see. Thank you. Yeah.
Video.
Yeah, thank you. Okay. So there's a lot more examples in the lecture notes. You guys can practice at home. And when you do try at home, please, again, we have this resource. Guys, just a second, please. So when you practice the examples at home, please don't be afraid to use ChatGPT to check your answers because we have that resource. Let's use it. So we don't have to practice in the dark, basically, like we used to back in my day. All right, then, guys, have a good long weekend. You think so?
Good Friday. So
I'll stop this before I tell you my age. You know my age. Yeah.